of that, Celine?
Yes. Hello. Thank you for the talk. I don't know too much on switches, but if I understood correctly, in the optimization problem that you solved on slide 12, you assume that the arrival rates are known, the lambda ij, and so I was wondering, do you have an idea of how performance is impacted if you only have an estimate of these arrival rates? For instance, you only know that they are in a given bound and you use these bounds to optimize, to solve the optimization problem?
Thanks. That's a very good question. We actually encountered that or different variation of that questions. Yes, the algorithm, the optimal algorithm, will depend on knowing the arrival rate exactly. Especially I think it's kind of in terms of the performance of the the fluid system, it will be kind of linearly depends on the error. So, for example, then you probably know the max weights policy does not depend on the knowing arrival rate. So you can, but you can from the numerical experiment we've done, you can see you actually gain lots of performance knowing the arrival rate. So knowing them precisely do help the algorithm. So it actually has quite significant impact.
If I could also add, it also depends upon the region of the fluid model. So as Yingdong pointed out, in some regions of the fluid model, the optimal policy performs as C mu, in which case it's not dependent upon the arrival rate. But then as the system enters regions, it does depend highly upon the arrival rate. So, but to your point, Salim, we have not studied the impact of the arrival rate on the problem. We were just trying to understand, because it is not known, what the truly optimal policy is. Thank you.
Okay, thank you. That helps.
Yeah, I mean that's actually quite interesting. It's quite an interesting question. It makes me think maybe some kind of perturbation analysis could be appropriate. But even without that, before you attempted that, then it'd be interesting to see some numerical results. The simulation just would change the parameters a little bit and see what a difference you get. Just purely pragmatic approach.
Yeah, that's a very good suggestion. Yeah.
So Isaac, please. Yeah.
Yeah. Hi. I was wondering whether this algorithm leads to a state space collapse. I remember a recent sequence of works that shows max weight in these input queued switches always leads to some kind of state space collapse. Relating to the vertices and facets of the stability polyhedron. Do you know if this algorithm leads to any state space collapse?
I cannot say. I think so. It's I can't say definitively. This actually is part of ongoing research. We were looking at the second order approximation of
the diffusion.
So that's part of the study. From so far, what we have seen, it does look like you can have similar state space collapse. Similar to max weight.
Okay, got it. Thanks.
Well, I just had one other idea about it, which is that so you've got these n squared queues, because one for each pair of input and output port. I just wondered what happened if there was the possibility of some queuing at the output ports in which case you could reorder at the output port. I was a little bit worried about the fairness in the. I mean, I know a lot of that can come out of the schedule and how you choose C and that kind of thing, but have you got any thoughts on that, or would it even be worth doing? I don't know if you have such switches where there's queues at the output ports.
Sorry.
You have queuing at the input, and they're separated for different output ports. There was different queue for each of the output ports.
Yeah.
So I wondered, well, if you allowed queues at the output ports as well, then you could send more than one at a time, then the output port could reschedule if it wanted to. It may be that no switch is ever made that way. I don't know enough about it, but it's just something that crossed my mind.
So currently the queue is for one. Each queue is for one input and one output.
Yeah.
So so we assume at the arrival you know which output you're going to do. Suggesting that
Okay,
you
so
can allow
you've got n-squared channels anyway, so effectively you do have output buffers in a sense of output ports. Yeah, okay, yeah, that explains it.
Yeah, you know that where you're going. But of course, you can relax that, allow multiple destinations. That will be a variation. Will be interesting to look at it.
Yeah, I was thinking in the physical switch where the queues are. Effectively, you've got what I was asking for. In your early diagrams, you had queues at the input ports, and then it looked like, well, some you wouldn't necessarily serve first come, first serve, but your answer's fine anyway for me, because you've got basically logically got n-squared queues. I suppose then the question is, no, that's fine. I think there's no more questions on Slack. No one's got their hand up